Hello everyone, this is Bidya. Me and my project partner Srizu, we are excited to share our project on loan approval prediction and optimization. This work highlights how predictive and prescriptive analytics can improve the loan approval process for a financial institution. Let's dive here. Let's outline the key aspects of our project. Our primary objective is to predict loan approval outcomes based on both financial and personal attributes of applicants. By doing so, we aim to streamline the loan approval process, making it more efficient and effective for financial institution. We decided to focus specifically on mid-income applicants, those earning between 50,000 and 100,000 annually. This group represents a critical segment for financial institution balancing risk and opportunity at the same time. So the significance of this work lies in addressing the institution dual needs, for example, ensuring efficient and accurate loan processing while simultaneously minimizing the financial risk. By integrating these analytics like predictive and prescriptive analytics, this project has the potential to create real value for the lenders and applicants alike. Let's move into the background research. To set the stage of our project, we conducted thoroughly a background research. First, we identified that credit score and loan amount are two well established predictors in loan approval studies. These variables play a critical role in determining an applicant's eligibility for a loan approval or loan application. However, some financial institutions face significant challenges. They need to process an ever increasing volume of applications efficiently while managing risk associated with the diverse applicant profiles. This growing demand and variation in applicant characteristics highlight the need for advanced analytics to ensure fair, efficient, and accurate loan approval decisions. So, our project main goal to address these challenges through predictive and prescriptive analytics. Let's move into the problem presentation. Now look at the core problems our project addresses. First, we have risk identification. Second, we have operational efficiency. And third, we have optimizing loan approvals. In the context of risk identification, loan applicants from high risk individuals often create delays in the approval process, as an institution need to carefully evaluate these cases to mitigate potential losses. So next, in operational efficiency, the current process relies heavily on manual intervention, which can be time consuming and prone to inconsistencies. So our goal is optimizing loan approvals. We aim to strike a balance between minimizing risk and maximizing profitability. So in this slide, we showcased our three analytics method and processes that we used in our project. First, we used descriptive analytics to understand historical patterns and trends in loan approvals. This step helped us to identify patterns and relationships within the data, such as the influence of credit score and loan amounts on approval decisions. Next, we applied predictive analytics to forecast our outcomes. And in this analytics, we used models like logistic regression, decision trees, and random forest. Here, we aim to accurately predict whether an applicant would be approved or rejected. So finally, we employed prescriptive analytics to optimize decision making. By incorporating budgetary and risk constraints, we used Excel and we used the method of sensitivity analysis, and we got the actionable recommendation to maximize the approvals while minimizing the financial risk. Here we included our data source and key variables. We got our data set from Kaggle's financial data, and this data set provided us with a robust foundation to analyze our loan approval patterns. We focused on several key variables that are critical for understanding on loan approval decision and loan approval outcomes. Here, we mostly use the applicant income and loan amount, credit score, and loan term. So for the applicant income, we assess the financial stability of applicants, and for the loan amount, we determine the repayment of loans, and we assess the risk. And in a credit score, we evaluate the applicant's credit worthiness, and on the loan term we insight into the duration of the financial obligation. On the next, once we acquired the data set, we focused on transforming it to ensure that it was clean, relevant, and ready for analysis. First, we conducted variable removal. For example, we removed the education level variable, which we found that it does not have significant impact on loan approval prediction. By excluding such variables, we improved the model's focus and efficiency. Second, we decided to avoid creating synthetic variables. So the original data set provided sufficient insights, and we prioritize simplicity and proper interpretation in our analysis. So this um step ensured that our data was optimized for predictive modeling while maintaining transparency and relevance. Moving to the next slide, we have our descriptive results, and this slide provided some key insights into the loan approval trends and the foundation for the predictive and prescriptive analysis. First, here we observed that loan approved loans generally have smaller loan amounts and higher credit scores. So this aligns with the expectation that applicants with a better score and manageable loan sizes are more likely to receive approval. The interesting fact that we found here is loan status is not strongly correlated with annual income, which suggests that while income might play a role, and other factors like again credit score and loan amount are more influential in determining approval decision. The bar chart in the right side shows the distribution of approved and rejected loans, which highlights the overall trends here in our dataset. These findings set the foundation for building our predictive models.
After uncovering patterns in the data, as Vidya mentioned, we will now move to predictive modeling to forecast loan approvals. To ensure that our predictive models were both accurate and reliable, we applied several tuning techniques. These techniques helped us optimize model performance, reduce overfitting. Let me walk you through the key steps we followed. We used 10-fold cross-validation. This was our first tuning technique, which is essential for evaluating the stability and performance of our model. The dataset was split into 10 equal parts. In each iteration, 9 folds were used for training the model and the remaining fold was used for testing. This process was repeated 10 times, with each fold serving as the test set once. Cross-validation prevents overfitting by ensuring that the model performs well across multiple subsets of the data. The second step in model tuning was predictor selection. We analyzed the statistical significance of each variable using metrics such as p-values in logistic regression and feature importance scores in decision trees and random forests. Variables like credit score, loan amount, and loan term emerged as the most impactful predictors. Conversely, education levels showed no meaningful contribution to loan approval predictions. Including only significant predictors reduce noise in the model and improves interpretability while also minimizing the risk of overfitting. During predictor selection, we identified education level as an insignificant variable. Our descriptive analysis showed no significant difference in loan approval rates between graduates and non-graduates. So we removed education level from the variable. Our goal was to build models capable of accurately classifying loan applications as approved or rejected based on financial and personal attributes. We evaluated 3 models: logistic regression, decision trees, and random forest. Each model was carefully tuned and validated to ensure robust performance. First, we applied logistic regression. Logistic regression estimates the probability of loan approval based on a weighted combination of predictors like credit score and loan amount. It achieved an accuracy of 91.54% and F1 score of 93.22%, indicating good overall performance. Next, we implemented a decision tree model which works by splitting the dataset into branches based on decision rules derived from the predictors. The tree begins by evaluating the most significant variables such as credit score and iteratively splits the data until it classifies each loan application. The decision tree improved accuracy to 96.42% and achieved an F1 score of 97.05%, indicating better classification performance than logistic regression. Finally, we implemented a random forest model which builds upon decision tree by creating an ensemble of trees. The random forest model outperformed the others, achieving perfect accuracy of 100% along with precision recall and F1 scores of 100%. So here is the slide that presents the confusion matrices for the three predictive models we evaluated: logistic regression, decision tree, and random forest. The left one is logistic regression, the middle one is decision tree, and the right one shows random forest. The confusion matrix provides a detailed breakdown of the model's prediction by showing true positives, which means correctly predicted loan approvals, true negatives, which is correctly predicted loan rejections, false positives, which is incorrectly predicted approvals, and false negatives, which is incorrectly predicted rejections. These values helps us evaluate the model based on their ability to minimize errors while maximizing correct predictions. Let's start with logistic regression. Here you can see that 2,481 applications were correctly classified as approved. 1,427 applications were correctly classified as rejected. 175 applicants were incorrectly predicted approvals for rejected loans. 186 where the model missed actual approvals. Logistic regression performed well overall, but the relatively high number of false negatives indicates that some eligible applicants were wrongly classified as ineligible. This limits its ability to fully capture the complexity of the data. Next, let's look at the decision tree. Here, true positives were 2,519 applications which were correctly classified as approved. True negatives, which is 1,597 applications which were correctly classified as rejected. False positives 137, which is slightly lower than logistic regression. False negative, which is 16, significantly reduced compared to logistic regression. The decision tree showed better precision and recall than logistic regression with fewer false negatives and false positives. However, its slight overfitting tendency may limit its ability to generalize. Finally, we have random forest. So here, true positives of 2,656 applications who were perfectly classified as approved. 1,613 applications were perfectly classified as rejected. 0 meaning there were no incorrect predictions for rejected loans. 0 meaning no approved loans were missed. The random forest model achieved perfect classification with 0 errors in both false positive and false negative. This makes it the most reliable model, particularly for high-stakes decisions where errors can have significant financial consequences. Here's how the tree model compare based on their confusion matrices. Logistic regression had more false negatives, meaning some eligible applicants were missed. Decision tree reduced those errors significantly but showed slight overfitting. Random forest outperformed by achieving perfect precision and recall, making it the most accurate and robust choice for predicting loan approvals. These confusion matrices highlight the strength and weakness of each model, while logistic regression and decision tree are simpler and interpretable. Random forest ensemble approach makes it the best performing model for this task. With the predictive analysis complete, let's explore how we optimized loan approval using prescriptive analytics. As we identified the best predictive model being random forest, we moved to prescriptive analysis to optimize loan approval decisions. The objective of this analysis was to maximize the number of approved applicants while adhering to institutional constraints such as budget limit, loan amounts, and credit score threshold. This analysis answers a critical question. Given the prediction, which loan applications should be approved to achieve maximum profitability and minimum risk? Our prescriptive analysis was conducted using the GRZ nonlinear method in Excel solver. This optimization algorithm is well suited for our problems that has complex constraints and multiple decision variables. Here's how we approach the optimization. The key variable influencing loan approval decisions were credit score. Higher score increased the likelihood of approval. Loan amount. Smaller loan requests were prioritized due to financial risk. Loan term. Shorter terms were preferred due to their lower risk. These variables were treated as inputs for the optimization function. Constraints. To align with institutional policies, we defined these constraints. Credit score were restricted to a range of 550 to 900. Loan amount was capped between $1 million and $4 million. Loan term were limited to a maximum of 20 years. Loan to income ratio was ensured to remain within feasible bounds, ideally between 2.5 and 100. Budget constraint, a maximum budget of $5 million was set for total approved loans. The objective function was the optimization aimed to maximize the number of approved loans while adhering to the constraints. The function used for optimization was based on predictive probabilities derived from the random forest model, prioritizing applicants with higher credit score and smaller loan amounts. To further refine our recommendation, we conducted a sensitivity analysis to evaluate how changes in income impacted loan approval decisions. Applicants with higher income were more likely to be approved, especially in the lower income range. However, the influence of income diminished beyond a certain threshold as credit score and loan amount became the dominant factors. This analysis provided actionable insights for tailoring loan policies to applicants' profiles. Our prescriptive analysis yielded these key results. The model approved the maximum number of applicants within the $5 million budget by prioritizing lower loan amounts and applicants with credit scores above 600. Higher credit score and smaller loan amounts had the strongest positive impact on approval decisions. Loan approval were optimized to balance profitability and risk, ensuring institutional policies were met. To conclude, our project demonstrates the power of data-driven analytics in optimizing loan approval processes. By combining descriptive, predictive, and prescriptive techniques, we successfully address key challenges faced by financial institutions. The primary outcomes are improved processing efficiency. Through predictive modeling, particularly the random forest, we streamlined the loan approval process, reduced cost. By focusing on high credit, low risk applicants, we minimize the financial risk associated with loan defaults, enhanced risk management. Predictive and prescriptive analytics allowed us to balance profitability with risk by accurately identifying high risk applicants and prioritizing low risk ones. Based on our analysis, we propose following recommendations. Implement random forest for predictive analysis and focus on high credit applicants for profitability. Overall, our projects provides a scalable and efficient framework for loan approval optimization. By implementing these recommendations, financial institution can enhance operational efficiency, reduce risk, and improve customer satisfactions. Thank you for your attention.